3.25 from the exercise. Following data are obtained at 0 degrees Celsius in a constant volume batch reactor using pure gaseous A. So gas phase reaction A is pure in constant volume batch reactor. Stoichiometry is A giving you 2.5 R. So 1 mole giving you 2.5. That means during the course of reaction, volume is increasing. And if you carry out this in constant volume reactor, gas phase, so it is 2.5 times final volume. That means pressure will go on increasing in the reactor, and if you have pressure gauge, you can get the total pressure data or measure the pressure as a function of time. Okay. Find the rate equation which satisfactorily represents this decomposition. Equilibrium concentration is appreciable, so the reaction is reversible. For simplicity, first let us assume the reaction to be of first order reversible. Okay. In the data provided, this is the data and these are our calculated values. Partial pressure in mm of mercury, you start with 760, that means 1 atmosphere. As a function of time, you go on noting these readings, pressure will fall, and at time t tending to infinity, t is equal to infinity, that will denote equilibrium pressure PAE, and equilibrium conversion can be calculated. Okay, so just for the purpose of calculation, I have taken this infinity as 600, some arbitrary value which is much higher than this last value. Okay, so at time t is equal to infinity, pressure PA is given as 150. So one thing is clear, that equilibrium concentration is appreciable value, so reaction is reversible. That means even at time t tending to infinity, complete A is not consumed or conversion is not complete, not equal to 1. So we know the reaction is reversible from the data, but to test with integral method of analysis, we'll choose first the simplest form, that is first order reversible. So minus RA is equal to K1CA minus K2CR. Though it is A giving you 2.5 R, we are considering first order reversible. First order forward rate is first order, reverse rate is also first order. So we know the integrated form, this we have already derived. Minus ln of 1 minus xa by xae is equal to k1 into m plus 1 divided by m plus xae into t. Okay. Here no R is initially present. You start with pure A. That means CR0 is by 0, CR0 by CA0, that is M. So M is also 0. So this is 0, this is 0. So simply you are left with K1 divided by XAE into T. So we have to test for this with this data. So what we will do, we will make y is equal to mx plot, no y-intercept. Now we will obtain the data. XA can be obtained from this 1 minus PA by PA0. We want this on y-axis minus ln of 1 minus XA by XAE. XAE value is known, that is 0.803. So this is y and time on x-axis. So when we plot this minus ln of 1 minus XA by XAE as a function of time, we get a straight line passing through origin. This is the best fit line with correlation coefficient 0.999. So almost the fit is perfect. y is equal to 0.158x. So slope, what is slope? K1 by XAE. So K1 will be slope into XAE. So slope is 0.158, XAE is 0.803. So we know K1 as 0.1269. Okay. This Kc is K1 by K2, and that is nothing but 2.5 XAE by 1 minus XAE, because stoichiometry is 1:2.5. Now how to do this? This we have seen many times. Okay. And that is nothing but Cr at equilibrium by Ca at equilibrium. So 2.5 into XAE, XAE is 0.803 divided by 1 minus XAE, 1 minus 0.803. This comes out to be 10.167. Okay. So K1 by K2 is known. So from that K2 we can find out K1 by 10.167. If substitute the value of K1 as 0.1269, this we get as 0.01248. So we know K1, we know K2. This, the form we have assumed first order reversible, and our data is fitting perfect. That means the integrated form of rate law first order reversible, which we have tested, is valid. So our rate law was K1CA minus K2CR. We have determined K1 and K2 values, so we substitute those values. So rate law can be reported as minus RA is equal to 0.1269 CA minus 0.01248 CR.